Physics in the Flesh fans, welcome back to the third installment of Magnets and Electromagnets. Earth is surrounded by a magnetic field. A. Where are Earth's magnetic poles? B. Explain how Earth's magnetic field contributes to the Aurora Borealis. And C. How can a hiker use Earth's magnetic field to identify directions? So let's start off by drawing the Earth. And I'm just going to go ahead and draw a sphere. Now remember that in space, Earth, it's not rotating, well, I can't say vertically because vertically doesn't really mean anything in space. But based on our point of view, the Earth is actually spinning on a bit of an angle. Okay, so it's actually rotating not vertically, but just a little bit off. And I believe that angle is just about over 23 degrees. So it's said many times that Earth's magnetic field resembles that of a bar magnet. Okay, so a bar magnet's magnetic field, just like any magnetic field for any magnet, comes out of the north and goes into the south. Now, let's say this is the orientation. Let's say this is Earth's magnetic north and this is Earth's magnetic south. Unfortunately, just like the direction of current was, incorrectly defined as the direction a positive charge would move, because scientists were always considering experiments with a positive test charge. Similarly, Earth's magnetic north pole is actually the geographic south pole. Okay, so this is the magnetic north pole, but it's also the geographic south pole. And we're not going to switch it all of a sudden. So unfortunately, we're stuck with the way it's already been done. So for me, living in Canada, I can't say that I live in the south because, oh boy, if you go outside, it's pretty cold. Okay, so geographic north pole and magnetic south. Just remember that they're opposite and you won't have a problem. So where are Earth's magnetic poles? The magnetic south is in the north and the magnetic north is in the south. Okay, so now part B, explain how Earth's magnetic field contributes to the Aurora Borealis. Now this is actually a very, very complex thing, and I'm going to explain it very briefly here, but there's actually a lot of interactions that happen that lead to this. And there's a lot of ways that the Earth's magnetic field is affected due to impacting charged particles from the sun. But like I said, for this video, we're going to keep it pretty simple. Okay, so this is only meant to be the grade 12/first year university level, so we'll keep it simple. So if we do consider the Earth's magnetic field to be that of a bar magnet, like I said earlier, the magnetic field lines come out of the north and they go into the south. So let's try to sketch some of those. So it comes out of north, goes into the south. Okay, and you can draw a few lines like that. Now, the more lines you draw, the further away they're going to get in this area here, towards the middle. So you can draw one more. It takes practice to draw these. And of course, the magnetic field is symmetrical. It's actually going in all directions, but we'll just show this based on a two-dimensional point of view. So there we go. And we'll do one more. Okay, and of course we've got it coming down here and going inwards like that. Okay, so there's the magnetic field of the Earth. It looks like a bar magnet. How does it contribute to the Aurora Borealis? Now, Aurora Borealis is actually the name of the light show given to the interaction of charged particles with Earth's magnetic field in the geographic North Pole. The word for it in the South Pole is called Aurora Australis. It's the same idea, and there's a reason why it only happens at the poles of the Earth. So if you actually look at this picture very, very closely, you'll notice that at the poles, the density of magnetic field lines, so if I draw a circle like this, notice that more lines go through that circle than if I drew the same circle out here. Right here I have 2 lines going through it. Here I have 5, almost 6 lines going through it. So wherever you have more dense magnetic field lines, the magnetic field is stronger. So the magnetic field for the Earth is strongest at the poles, and therefore it's weakest at the equator. So what happens is the charged particles from the sun, so I'm not going to be writing this down, I'm just going to explain it. But again, this is a very complex interaction, but generally speaking, the charged particles that are coming from the sun, so we can call that the solar wind, these charged particles are heading towards the Earth, and they enter where the magnetic field is the weakest, so near the equator. Now, once they enter and combine with a sufficiently strong magnetic field, right, they start following that magnetic field line towards either one pole or the other, depending on whether the charge is positive or negative, right? So then you can use the right-hand rule to determine which way it would go. Okay, so let's say our charged particle heads towards the geographic North Pole, magnetic South Pole. So it travels along these magnetic field lines until it gets to this area where the magnetic field is sufficiently strong. Okay, so at this point, the particles from the sun are going to interact and collide with the atoms here. And because the magnetic field is so strong, there's going to be a high amount of collisions. And these collisions give off a fantastic amount of light in various colors, hence the Aurora Borealis. Okay, so it's the collision of the particles from the solar wind with the particles near the poles that give off this fantastic light show. Okay, so that's the answer for part B. For part C, how can a hiker use a magnetic field to identify directions? Okay, so if you're lost, and honestly all of our technology now has this, we use a compass, right? So if you have a compass, it's supposed to point towards the magnetic North Pole. So of course, we're used to that compasses point towards the north, the geographic north. We're not told that's not the same as the magnetic north. So in fact, these compasses must be, I guess, reevaluated or modified so that they actually, the way they make this part, it doesn't show that it's pointing towards the magnetic north. It just shows that it's pointing towards the geographic north. So they just have to design this so that the arrow looks like it's pointing in the opposite directions. So they'll put more emphasis on this side than they would on the other. Otherwise, people would be thinking they're going north and end up in the Caribbean. So that's it for this video, guys. I hope you enjoyed it. Be sure to stay tuned next week for video 172, Magnetic Force on Moving Charges 1.